Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you again for these students, and just ask you to bless our work today, Lord. In your name I pray. Amen. So if you turn in your homework, like pass it to the center and then pass it up. If you don't have a folder with your name on it, you should. That just means you missed the day that I handed them out, and the day after that, and the day after that, or something like that. But I will find you. If you're such a person, you're in here somewhere. I don't know, maybe those people are actually not with us anymore. Oh, thanks. Suspicious. So anyway, thank you for turning those in like I asked. That helps me turn them back to you and keep them sorted, you know. So today and Monday we have to talk about solutions to the mission and also, of course, the math battle, right? So I have the solution to the mission here, right? I don't have a solution for the math battle assembled yet, but I'll have it before Monday, I'd imagine. Probably sooner than that. So is there any particular question that you guys would like to talk about before I just dive in? I can go just from the start and all the way through, but if there's a particular problem that somebody wants to talk about, I should probably go to that.
It's not like a bigger problem, but are the test questions going to be very similar to the ones on the mission, or is it going to be like more of a cut down version?
Well, I mean, the point of the homework is to understand concepts, and the test should test the same concepts. Whether or not they're exactly the same style of problem or not, I haven't decided yet. But, you know, some of these, especially if it involves numerics, right? Like I can't do that on the test. You guys don't have a graphing calculator or a phone to work with on the test, right? So graphing you have to do by hand, whatever there is there. But yeah, I mean, okay, for example, the problem 4 would be kind of tough for the test, at least if you interpret it in the most sort of aggressive way possible. Let me put this top hat away. Oh, I said the words. All right. Other question? Yep. 6. So to understand 6, we have to go back to 5. So problem 5, I asked you to find the line segment from 3,5 to minus 213 using 0, 1 as your domain. So I use the pretty standard trick. I take the initial point, right, plus t times the difference of the points. And sorry, I try not to burn that onto your retina at the moment. So I don't know why the green lasers are so much brighter. Question of solid state physics, I think. But anyway, so I got 3 minus 5t, 5, comma 5 plus 8t for the parameterization of the line segment. Of course, it is equivalent to writing the equations x equals 3 minus 5t and y equals 5 plus 8t. All right, for 0 less than t less than 1. So this is the parameterization of the line segment. Is that clear? Okay. So I use that in problem 6 because what I have, of course, is this, you know, this wheel, right? And I told you guys in class that it was glued, the center was glued along the line segment from problem 5, and then it's rotating 20 times per second, right? So I told you the initial position of the light was at 5,5, which means that relative to the, the wheel, it is at 0 degrees, so to speak, for the angle measured relative to that axis on the wheel. So I can just focus my attention on the wheel for a second and parameterize that. It's something like R2 is equal to 2 cosine theta, 2 sine theta, where theta is the angle it's sweeping out relative to the horizontal of the wheel, and you can just imagine that horizontal kind of tracking up with the wheel as it goes. And then I can make theta equal to omega t plus delta, like different choices of omega and delta will tell me how fast it's going and like its starting point. This is just the simplest possible thing you could put for the angle. It's a linear angular velocity if you make omega a constant. So if we make omega the angular velocity 20 pi, that will cycle through 20 revolutions in 1 second, right? If I go from t equals to 0 to t equals to 1, I cycle through 20 pi worth of angle, which is to say 10 revolutions per second, right? Did I say 20? I meant 10 revolutions per second. And the other thing, of course, is I choose delta equal to 0 because I want the light to initially be there, right? So just to double check, if I plug in t equal to 0, I get 2 comma 0, which means that I go from 3,5 plus 2 comma 0 over to 5,5. So that's like my starting point is that. And then, of course, at time 0 also, although not pictured, R1 of 0 points to 3,5 as well, right? So R1 is the parameterization of the line segment from problem 5. So the idea was to take the line segment and then add the displacement relative to the wheel. Put those together, then you're tracking along this wheel that's going up like that. And so that gave me these. And then once you have this, the velocity, acceleration are a breeze, right? Just differentiate. Yep. Oh yeah, of course. Yeah. No. Yes, this I post in course content. I don't expect you to copy these down like madmen. No. Or women. 2019. Fun observation. The acceleration, you can factor out 800 pi squared, right? And then you've got this, which is a unit vector that points towards the middle of the circle. So it's like the acceleration's pointing towards the center of the circle as it's rotating. And the significance of the magnitude of the acceleration, 800 pi squared, is its r omega squared, which you maybe would recognize from physics 231 in the future. Once you get to the final chapters on rotational motion, you'll learn this formula for acceleration, the linear acceleration of a constant. If you have constant angular acceleration, maybe you've seen this formula before as v squared over r, the centripetal acceleration. If you convert that to angular velocity, v is equal to omega r. So you get omega r squared over r, which simplifies to omega squared r. Anyway, just fun observation. Obviously, I don't expect you to know that sort of thing in here. Let's go back to the start. So problem number 1. My apologies. I worked this one out in class, right? My bad. I should have put like cosh inverse hyperbolic cosine on the homework if I was going to do sinh in class, right? So, how would you do if instead of having cosh inverse I had sinh inverse? What would the difference be? Plus, right? There'd be a plus there, but otherwise the mathematics is kind of about the same. Inverse hyperbolic tangent, on the other hand, is really a little bit kind of different, and I worked that out somewhere. But anyway, I don't actually expect you to have these memorized, all right? So if I wanted you to use these in the test, I would state them or ask you to derive them, all right? But these are not something I expect you to have committed to memory, in contrast to many, many things. Problem 2, I asked you to derive the derivative of inverse sine. And so, just a little bit of background, this is what sine looks like relative to where we invert it, right? It goes from pi over 2, minus pi over 2 to pi over 2. inverse sine is actually the local inverse of sine restricted to that domain, which is why the range of the inverse sine is that domain. It's minus pi over 2 to pi over 2. Anyway, usual song and dance, implicit differentiation, we get 1 over plus or minus the square root of 1 minus x squared from the algebra. Why do you choose the plus? Well, generic comment. If we differentiate the inverse, like f inverse of f of x, this is the condition for a function being the inverse function, right? If you differentiate this, the chain rule gives you this. So what this says is that the rate of change of the inverse at x, the rate of change of the inverse where? Not at x, but at f of x, has to match the rate of change, well, it doesn't have to match, but it has to be related to the rate of change of f at x. In other words, the product of these has to be 1. So if you think about that, that means that they have to both be plus or they have to both be minus. If the function's increasing, the inverse function has to be increasing. If the function's decreasing, the inverse function has to be decreasing. All right? And by the way, there can't be a point where the function has 0 derivative. Why? If you're inverting it. If you had 0 derivative, that means you're at a turning point, right? You don't have the one-to-one property there. You can't find the inverse relative to a point where you've got a 0 derivative. So there's no loss of generality here. The function, if we're going to find an inverse for the function, it has to be either increasing or decreasing on the domain of consideration. And likewise, the inverse function has to have the same behavior. So since sine is increasing from pi over 2, minus pi over 2, pi over 2, obviously, you can see it, right? It follows that we must choose the plus because the inverse sine must also be increasing. This is the logic behind choosing the plus. You know, if you had this and you didn't have all of this, you'd still get, 80% of the credit. So, but we should understand why things are true, okay? Problem 3 hopefully was pretty cut and dried. For those of you who are currently taking Physics 231, you should be like beyond bored with this problem, right? But here it is. So if we have a vector in 2 dimensions, the way to figure out the standard angle is to draw a picture. You must draw a picture. If you do not draw a picture, odds are you're going to get it wrong. Because if you just blindly take inverse tangents of y over x components, it's only right half the time. The inverse tangent only gives you right angles in quadrants 1 and 4. Inverse tangent of the y over the x component is wrong in quadrants 2 and quadrants 3. So that's why I draw this picture and find the reference angle beta. So that beta is inverse tangent of 1/3, 18.43 degrees. And then I'm like, okay, so 270 goes all the way over here. I have to just remove beta from 270 to get the standard angle, which is from positive x-axis around counterclockwise sense, which is why I get 251.57 degrees. All right? The unit vector, you just divide by the length, that is the magnitude. And so here it's minus 1 over root 10, minus 3 over root 10. You could leave the 1 over root 10 out front of the vector. That wouldn't change the answer. In some sense, I prefer leaving if you can factor something out and leave it as multiple, that's better in some sense. To find the angle between the vector and 3, 9, we can use a dot product. So like the dot product of u and 3, 9 is minus 30, but this is also 30. So what you're looking at is cosine gamma equal to minus 1. I lost my minus. Dang it. Oh, man. Well, this is wrong. What should that be? What's that? Yeah, 180. It's like the most wrong it could possibly be. It's the farthest away from the correct answer possible. That minus matters if it's, and you can see this. If you look at this, that is minus 3 times the first vector. Right? So it's the 3, 9 is actually minus 3 times 1, excuse me. If we take this and we divide by minus 3, we get that, right? These are scalar multiples, negative scalar multiples of each other, which means that they're directly opposite. All right, anyway. Let me stop majoring in the minors here. I mean, vectors and angles between vectors are at most 5% of your test, all right? It is something I think you should know. It's edifying for you to learn that now and just settle it for yourself because it's something you need to know, whatever your major is here. Now, so this one here, 3, 4, I calculate this standard angle, that magnitude, that unit vector. I found the angle between them was 8.13 degrees. And anyway, any questions about this? I think I'm going to go on to the next problem. The main thing here maybe that you should pay attention to is that, in this case, I could use inverse tangent, right? That makes sense because I'm in quadrant 1, so the reciprocal, the opposite over the adjacent, that does give me tangent theta there. Over here, though, tangent beta is actually that angle. It's not the standard angle, which is from over here. This is why you should not install observation decks over rooms with ceiling hanging projectors, right? So if you're ever designing a university, keep that in mind. All right, problem 4. Let me move on here. So I actually, I think you guys would respect this solution. I took a 30, 60, 90 protractor. I carefully graphed this point and that point using a centimeter per unit. And then I took the protractor and I took the 60-degree angle and I fit it and found this point. And then I measured the length relative to my scale and found that that point's about 0 minus 0.25. So there's an answer. No calculus. Sorry. Actually, there's no calculus in this problem, right? This is just a geometry problem, is it not? But remember, this is calculus 2 with what? Analytic geometry. This is that analytic geometry. Analytic geometry is where geometry and algebra meet, right? So, that only gives me an approximate answer. I think a better way to do is to look at the vector A like that, the vector B like that. The dot product of A and B has to be AB cosine 60 for the point that we want. So that gives me 2A dot B is equal to AB, which gives me this equation. And then any solution to this is going to be the kind of point we're looking for. And I'm sure you guys made various simplifications to make this easier to solve. Like I pointed out, you could reasonably have set A equals to 0. That would have given you a solution that happened to be on this right here, right? You could have also put B equal to 0. It would have given you the solution that's over here somewhere or over there somewhere. There are infinitely many solutions to this problem, though. It is, of course, a challenge problem. All right, moving on. We talked about 5 already. 6, 7. Now, getting back to your question about what's most test-worthy, 7 is definitely something I have asked on the test before. All right? So I am completely likely to ask you to parameterize and graph ellipses, hyperbolas, circles, line segments. All right? So actually, if you look at old tests, like if I can find one. Let's see here. How about this is test 4, but you notice I've moved your test 4 stuff to test 1 in part. I mean, you only have 3 tests, right? So it's hard to see on my scan, but on your actual test, there's like a very light grid for you to graph something over. If I ask graphing, I usually provide that as part of the problem for you to kind of work over, right? And then, of course, typically you guys choose a completely ridiculous scale and make your picture like this part of it. Drives me crazy. Anyway, let me get back to my... There we go. So this kind of problem, complete the square. Once we have a sum of squares, it's an ellipse, or a circle in this case, because the same constant for both squared terms, right? So once I see that, that tells me I can put minus 1 plus 4 cosine t, because there's a 4 squared over here, and 3 plus 4 sine t, again, because there's a 4 over here, and there's a minus 3 there. And to check, of course, if you put x equal to that, if you put y equal to that, you plug them back in, you'll get 16, right? Now, I also told you x was greater than or equal to 1 here, which means if we graph the circle, it looks something like this. Just this arc of the circle is all we want, right? So that means I need the x, which in this case is minus 1 plus 4 cosine t, to be greater than or equal to 1. That is equivalent to condition 4 cosine t greater than or equal to 2, which is the same as cosine t greater than or equal to half, which I can see by graphing cosine and looking for the part of cosine which is above a half. That is exactly from minus pi over 3 to pi over 3. That's the solution to that. So the domain that I should choose for part A is minus pi over 3 to pi over 3. That will trace over just that part of the circle. Yeah. Part B, there was no completing the square. It was already completed, right? So we got a difference. That's a hyperbola. We use cosh and sinh to parameterize this. By default, we'll just rattle off x equals to cosh, y equals to sinh for this kind of pattern. But then I do some soul searching and go, wait a minute, that doesn't work because x is what? Yeah, x is given to be less than 0, but this x is greater than or equal to 1. So this won't do, but that's easy enough to fix. We just slap a minus on the cosh. And if you think about it, putting a minus on cosh still will satisfy this, right? We'll still have cosh squared minus sinh squared be 1. It still works, and it's got the necessary, it's on the necessary branch. So this parameterizes this branch of the hyperbola. The thing I wrote down to start with is actually the parameterization of that one. Right? Yep.
When you're graphing hyperbolas, what do you like reference in the functions? Like, know how? I don't know how to graph a hyperbola very well by hand.
Don't know how to graph a hyperbola very well by hand. So a reasonable question. Let me take 5 minutes. Talk about that. So what does a generic hyperbola look like? Generically speaking, it looks something like this. X minus h squared minus y minus k squared divided by a squared divided by b squared equals to 1. I mean, that's one possibility. So if it looks like this, if it's x squared minus y squared, what happens if you put x equals to h? You get minus a real number squared equals to 1. I mean, look at the, right? If I put x equal to h, this is 0, and this is minus the square of something. Can you have minus the square of a real number be 1? No, I mean, we can't do that, right? Which is to say, let me just erase this and just say, set x equals to h to see no solution there. What's that mean? So the graph does not cross x equals to h. So that's the first thing I check to figure out whether the hyperbola is opening sideways or vertically. Once I learn that it doesn't cross x equals to h, I know what kind of hyperbola I'm looking at. I'm looking at one that opens horizontally. All right? And it doesn't cross the, let's say h is positive, x equals to h, right? Next up, what happens if x and y are really big? I mean, asymptotes for this, well, let me just say this. Asymptotes, we can, I need another color. Ignore the 1 and just solve for, to find the asymptotes, we have something like this. Y, yeah, I just said y minus k squared over b squared equals to x minus h squared. This is not actually a solution. This is not actually something on the hyperbola, but it tells me, this will give me the equations for the asymptotes for the hyperbola. In particular, this gives me y is equal to k plus or minus b over a times x minus h. So that is to say that the asymptotes, they go through the point h comma k. H comma k is the center, all right? So if this is k, I really shouldn't even, oh well, it's too late. Y equals to k. So the asymptotes of the hyperbola, these guys, look something like, they go through the center like that. Again, that's not part of the hyperbola itself. The hyperbola then is enveloped between these asymptotes, right? And the asymptotes, let's see here, what are the vertices? What are the turning points of the hyperbola? Plug in, I want to find where, to find where it crosses here, I think about y equals to k. Y equals to k, that's gone, right? And you've just got x minus h squared equals to a squared. So x is equal to h plus or minus a. So like this or that, let's say this is h plus a, like that. And then over here, h minus a over there. And the brown is actually the hyperbola. Example, if we had, say, x minus 1 squared over 9 plus y squared over 2 equal to 1, the center is where? 1, 0. What are the asymptotes? So all basically you do is ignore the 1 and solve for y to find the asymptotes. So ignoring the 1 and solving for y gives me plus or minus 3/2 x minus 1. Those are the asymptotes. And so 1, 0, somewhere out here, let's say, slope of 3/2 is kind of, that's 1.5 slope, right? So that's something like, I don't know. And where are the vertices for this thing? Put y equal to 0. 1 plus 9. I think one's at 10. Sorry, this is too, it's, oh well, I have chose a very poor scale for this graph. I mean, it's opening very, it's hard to see what's, I mean, I'd have to draw a lot more to see where the, it's going to be a while before this thing starts to get close to the asymptote. But that in a nutshell is how to graph hyperbolas. You got to find the asymptotes, identify the center, identify the vertices. If you do that, then you've got a pretty good picture of the hyperbola. Yeah.
So the vertices in this point, how to get that is just
The vertices, there'd be, in this, you put y equals, in this one, y equal to 0, gives me x minus 1 squared equal to 9. So x equal to 1 plus or minus 9. Oh, I'm an idiot. Square root of 9. Oh, I'm bad. Oh, I skipping steps is hurting me here. Thank you for that question. So it's 4 or what? Minus 2. Yeah, oh yeah. Well, actually, I thought that was 10 relative to that being 1 because I'm an idiot. That actually is about where it is. And actually, my picture is still right. It's just I don't understand what 10 versus 1 means on my current scale. Yes.
What's the difference between the minus top and the plus bottom?
What is the difference between the minus? Oh, good grief. That is supposed to be a minus. Thank you. Yeah, if with a plus there, that's an ellipse. Yep. Yep.
Can you just kind of just writing the general equation for an ellipse?
General equation for ellipse, something like x minus, I'll use hk for the center again, x minus h squared over a squared plus y minus k quantity squared over b squared equals to 1 is an ellipse with center hk and that point would be like y equals, h plus a comma k. This point over here would be h minus a comma k. The vertical, the high point and the low point for this guy would be h comma k minus b up here, h comma k plus b. That's it. And let me make the ellipse red. Now, you said write the general equation for an ellipse. Truth be told, this is not the general equation for an ellipse, because what else is possible? Like, I don't know. Is this an ellipse? I mean, up to the limits of my artistry. That's an ellipse. It's just rotated, right? So if you write the equation for something like that, it picks up cross terms. It's something of the form, something like ax squared plus bxy plus cy squared equal to 1 for appropriate choices of a, b, and c. You can get something like that. Why would this not be on the test? Because it's past its course. In order to understand that kind of an ellipse, you have to understand how to rotate coordinates, all right? You can find a rotated coordinate system where in the rotated coordinate system, which I could draw like this. Well, you can put x bar squared over a bar squared plus y bar squared over b bar squared equals to 1. There's another coordinate system where you can recast the equation of the ellipse in the standard form I just mentioned. But this we don't know yet, right? So for you guys, that's the general equation for an ellipse. Okay, let's get back to the party. There we go. All right. Oop, nope. Okay. All right. Moving along. Let's get to integration, yeah? So here's these pesky reversals. You know what, guys? No reversal on the test. We have talked enough about this. I know it's confusing to you guys. Invest your energy on the basics. Do not worry about reversal, okay? We'll get back to that in Calc 3. That's an empty thread. I'm not teaching Calc 3 next semester. Let's see here. I don't know. Maybe I am, actually. I really don't know. Problem 9. Problem 9. We had x equals 1 over t, y equals t squared plus 1. Part A said find the Cartesian form. So basically, I just took the first one and said, well, t is 1 over x, and then plugged it into the second one. And there you go. Y is equal to 1 over x squared plus 1, which is the volcano function shifted up 1, by the way. Do you guys know what I'm saying? You guys know about the volcano function? Yeah. Oh, that's the technical term. If you don't call it the volcano function in a publication, they'll like laugh you out of the room. Like, you can't publish this. You haven't called it the volcano function. That's its official technical term, yes, of course. I'm working on lying so that I can be a politician one day. It's not a lie if you believe it, right? I mean, we all have our own truth. Yes?
Conveniently in my homework, that's my truth, so we have to separate.
Oh, okay. Well, that depends on how much time I have for grading. Let's see here. So if that's the Cartesian form of the curve, of course you guys know how to find tangent lines, right? You calculate dy dx, that gives you the slope. You take the slope, you put it in to make the tangent line. There it is. On the other hand, the colliding tangent line is by definition parametrized to be L of t is r of 1 plus t minus 1 times r prime of 1. The reason for this formula is very simple. When t equals to 1, we have r of 1, which means at time 1, this path and the given path collide, right? And then this is a tangent line because it takes direction r prime of 1. This is the colliding tangent line. I would like you to know about this for the test, all right? Anyway, so I calculate this for the given path. Here's my path, here's my velocity. I plug in time 1. It gives me 1, 2 from this one. It gives me minus 1, 2 from that one. And then I just plug in the data into the general colliding tangent line parameterization, and there it is. I'm trying to get to integration. I will get to integration. I guess we still have some parametric stuff to settle. So I hope you looked at this parametrically. If you changed this to a Cartesian problem, it makes it way harder. I know some of you were thinking that way. I'm not sure I found all of you before it was too late. There's at least 3 different people in here working in Cartesians for this problem. No. Es no bueno. Horizontal tangent is where dy dt is 0. And we also need dx dt to be non-zero to make sure it's a tangent and not like a stopping point or a cusp or something weird. But of course, dx dt is e to the t, which is non-zero. So in fact, yes, cosine of t is 0, only for pi over 2 between 0 and pi, right? That's what this is over here. I'm thinking about cosine. Where is it 0 between 0 and pi? Just in the middle. So t equals to pi over 2 is the relevant parameter, and that gives me the horizontal tangent of y equals to 1. That is the horizontal tangent, right? Vertical tangent would require the dx dt was 0, which is impossible, no vertical tangent. This is the arc length. This is the integral of the speed, which is the square root of the components of the velocity squared added together, right? Which I got 22.4 with Wolfram alpha. And the surface area is 2 pi y ds, which in this case is exactly this, and I got 76.46. So if I ask this question on the test, how do I do it? It's pretty simple. I say, set up, but do not evaluate an integral for the surface area or for the arc length. If I say, set up and do not evaluate, and then you try to evaluate, what does this do? Does this make me respect you as a student? No, this makes me pity you. But like, it's the, do not, please read the instructions. Please read the instructions. Problem 11, I would say it was like taking candy from a baby, but if you know any babies, this is not a good saying. Taking candy from a sleeping baby, arguable. depends on how restless they are. But acceleration, we just differentiate. You got it. To find the position, we have to integrate. All right, so we do the integral. I did an antiderivative, which means I added constants. Notice we have to add a different constant for the x and for the y. Then I have to plug in 0. When I plug in 0, cosine of 0 is 1, so this gives me -1. And plug in 0 to that, well, I get 0. So I get this comma that. That has to be equal to the initial position, which is given to be 2, 1. And so that gives me C1 minus 1 is equal to 2, and C2 is equal to 1, which is easy to solve. C2 apparently is 1. And this, on the other hand, indicates that C1 is 3. So there you go. That's the position as a function of time. I like problem 12. It's kind of somewhere in between some just elementary analytic geometry and calculus, right? It's the merger of these two things. So if you think about being parallel to y equals to x, that's going to be points on the curve which have slope 1, right? So to find the points with slope 1, we can use dy dx as a function of time as dy dt over dx dt, which in this case is that. I set that equal to 1. That gives me a quadratic, which I can factor. I get t equals to 1 or t equals to 2. Then I take those parameter times, I plug them back into the parameterization to find the points in question, namely -1/2, 1/3, or 2 8/3. So if you found your way to t equals to 1 and t equals to 2 and you put that as an answer, I mean, it's not technically correct, but I also respect it as a good, I mean, your heart's in the right place, but you're just not done, So yeah, the Ninja Bob problem. So by my calculations, it's debatable. Like it happens right at the 2-minute mark if we're working in minutes. So, I mean, I think you could go either way depending on how you interpret. I mean, it's right on the cusp of, is it like a little bit less than 2 minutes it takes him to prepare, or is it a little bit more than 2 minutes, or is it exactly 2 minutes? And what happens if he meets it exactly 2 minutes? That's the question that's begged by this problem, because that's what it worked out to, for me. But there are various variations on this problem. You should try to have clear in your mind the distinction between collision versus intersection, right? Intersection would be possibly different parameters they're meeting, right? Collision, on the other hand, is the same time the two paths meet. Intersection is easy enough to find if you just find the corresponding Cartesian equations and solve them simultaneously. So that's what I did here. I just found y equals that for Bob and this ellipse equation for Sky. Solve those simultaneously. It ends up giving you x equal to 0 and x equals to 2. Once I know that, I can go back in and find the time when we got there. Easy enough to find for Bob. And once I find those times, then I can plug in, where. Well, first of all, time 5/4 is not relevant. We already know Bob's not ready to attack. Who cares about that point, right? But time 2, well, that's possibly relevant. So I plug in time 2, I get these 2 points, and uh-oh, look, they're at the same point, which means time 2 is, in fact, a collision point. So, all right. I will get to integration. Probably Monday. Okay, so this one was interesting. And so I said to analyze concave up and concave down for the curve, right? So we have to calculate d squared y dx squared. The way to do that is to, well, like so. So I found dy dx as a function of time, which gave me minus 2/3 tangent. And then I take the derivative of minus 2/3 tangent and divide by dx dt. That's how to calculate the second derivative. Or you could use the formula in my notes. Anyway, we should all agree that at the end of it, you get minus 2/9 cosine cubed. Your formula could have looked uglier, possibly. But if you look at this, it's never 0, right? It could be undefined if cosine's 0. And so I can make a sign chart to analyze where this is positive and negative. And my sign chart, of course, 0 and 2 pi, that's the edge of the world for us, because that's where t is allowed to go. And we have zeros at pi over 2 and 3 pi over 2. You plug in some points, you'll find that this expression is negative in here, it's positive there, it's negative over here. All right, so concave up between pi over 2 and 3 pi over 2, concave down for 0 to pi over 2 and 3 pi over 2 to 2 pi. Geometrically, this makes good sense because if we look at the path, it's exactly what you want. See, I use some color coding here. 0 to pi over 2 is this piece. 3 pi over 2 to 2 pi is over here. This is actually t equal to 0. It starts there because of the way the thing was parameterized. And so this is concave down, and down here, concave up. I think that's very geometrically reasonable, right? Finally, integration. Well, we got 2 minutes. Let's see what we can do. So is there any particular integral that was vexing that you want to talk about today before we go? These should be pretty standard. I mean, this could catch you off guard, but now that I've put this in your homework, if I put this on the test, it should not be a trick question, right? If this didn't happen in the homework and it just appeared on the test, in some sense I feel like this would be a trick question. But at the moment, it's just an invitation for you to think about laws of exponents, if you haven't recently. Square root of e to the x is e to the x to the 1/2 power, which is e to the x over 2. And of course, this is e to the minus x. Both of these are just plain u substitutions. Sine squared is a standard example. Sine cubed should be a standard example. Problem 17, most of the trouble is just somehow either finding or deriving this trig identity. After you know that, you can integrate it. When you do that, when you plug in pi, you get sine of a multiple of pi on either bound, which maps to 0. And when they're equal, you get pi. Just as a parting thought before you go this weekend, you can summarize the result. We have that the integral of sine px, sine qx from minus pi to pi is actually pi Kronecker delta p comma q. What this actually shows is that these functions, in some sense, are perpendicular if p is not equal to q. There's some generalization of the dot product that has to do with Fourier analysis. We'll talk about at the very end of class. And this calculation actually has a deep significance in terms of breaking music down into some kind of mathematical format which you can store on a computer, and like MP3s and stuff like that. Anyway, happy convo to you all. I will post this in course content.